The design of jet transport aircraft is biased towards maximum efficiency at high speed. Unfortunately, they will also have a high minimum operating speed, and even the most efficient trailing edge flaps will not reduce the takeoff and landing run to acceptable values. Therefore, jet transport aircraft must also be fitted with leading-edge high-lift devices, known as flaps or slats. This lesson will examine the three main types of leading-edge high-lift device in detail, in their order of increasing efficiency. Being the least efficient, we will begin with the Kruger flap. The illustration shows a cross-section through the leading edge of the wing. You can see that the Kruger flap forms part of the leading edge lower surface. When fully out, the Kruger flap gives a smoother path for the airflow over the leading edge of the wing, allowing the airflow to retain maximum kinetic energy. Kruger flaps are either in or out. There are no intermediate angles like trailing edge flaps. Operationally, leading edge devices are usually used together with the trailing edge flaps. But for reasons of clarity, only leading edge devices will be illustrated. There is usually only one flap lever on the flight deck. When the flight crew makes a flap selection, an aircraft system will schedule the leading edge devices to operate in conjunction with the trailing edge flaps at the appropriate time. In this example, a selection of flaps 1 activates the Kruger flaps. They will remain fully out until the flaps are selected from flaps 1 to flaps up during retraction. With the Kruger flaps out, the camber of the wing is increased. And as you can see, CLmax is increased. In addition, the forward end of the chord line is lowered, which increases the stall angle. The next type of leading edge device to consider is the variable camber leading edge flap. The variable camber is more efficient than the Kruger flap. The reason for its increased efficiency is that the variable camber leading edge flap has a mechanism that curves the flap surface as it extends. When fully out, the variable camber flap gives an even smoother path for the airflow than the Kruger flap, allowing maximum retention of kinetic energy in the boundary layer. Again, there are no intermediate selections possible. They are either in or out. In practice, their speed of operation is about twice that illustrated. With the variable camber leading edge flaps out, the camber of the wing is increased slightly more than with the Kruger flap. And as you can see, CLmax is also increased. The forward end of the chord line is once again lowered, which increases the stall angle. Now we come to the most efficient leading edge high lift device, the slat. To illustrate the effect of slats, a wing is shown at a high angle of attack, with the airflow just starting to separate at the trailing edge. The aircraft is positioned on the lift curve. As the slats are driven open, high-energy air from under the leading edge flows onto the top surface of the wing. This increases the kinetic energy in the boundary layer, which in this example reattaches the airflow. Slats increase CLmax by increasing the boundary layer kinetic energy. This merely extends the lift curve. If a constant angle of attack is maintained, the lift coefficient of the aircraft will remain the same, and there will be no operational change. For the aircraft to benefit from slats, the pilot must fly the aircraft at a higher angle of attack, a higher nose attitude. There are two disadvantages with the higher nose attitude. Firstly, when rotating the aircraft for takeoff or flaring to land, there is an increased tendency to tail strike. Secondly, there is reduced visibility from the flight deck when approaching to land. Here, we can see a sketch of the low-pressure area on the top of the wing, with the aircraft at a high angle of attack. Suction is reduced towards the trailing edge because of minor airflow separation. When slats are driven open, we know that the increased boundary layer kinetic energy reattaches the airflow. The low-pressure area becomes more evenly distributed, but the total area changes very little. Please note that the suction peak does not move forward. so the effect of slats on aircraft pitching moment is insignificant. Some jet transport aircraft have an automatic system that will fully extend the slats for stall protection. If the aircraft approaches the stall angle too closely, the automatic slat system will extend the slats to the fully open position. This illustration shows the order of increasing stall angle for flaps. The configuration that gives the lowest stall angle is trailing edge flaps. The next higher stall angle is no flaps, and the highest stall angle is leading edge flaps. This is not an operational consideration, but the examiners might ask you. If a flap selection is made, and, due to a fault of some kind, only the flaps on one side move, the rolling moment generated can be greater than the pilot can oppose with roll control. Flap asymmetry must be prevented. To avoid the possibility of flap asymmetry, transport aircraft are usually fitted with a flap asymmetry protection system. Devices monitor flap extension angles on each half of the wing, and if an asymmetry of greater than 1 or 2 degrees is detected, the mechanism that drives the flaps is switched off, and a warning on the flight deck will alert the pilots. Transport aircraft can be fitted with a flap load relief system, which prevents the flaps deploying if the indicated airspeed is too high. The pilot can move the flap selector, but the flaps will not extend until the indicated airspeed is reduced to the value appropriate for that flap setting. These flap angle limiting indicated airspeeds are known as VFE. Excessive dynamic pressure can damage the flaps themselves, their hinges and operating systems, or the wing. In this example, flaps 25 has been selected at too high an indicated airspeed. In other words, above VFE for flaps 25. The flap load relief system prevents the flaps from moving. The aircraft is now slowed to VFE for flaps 25, and the flaps move down to 25 degrees. The indicated airspeed is now reduced to VFE for flaps 30. When flaps 30 is selected, the flaps move down to 30 degrees. But if the indicated airspeed is allowed to increase, the flap load relief system will drive the flaps back to flaps 25. If now the indicated airspeed is reduced to VFE for flaps 30, the flaps will move down to 30 degrees of flap again. Here, we will only consider the effect of flaps on the takeoff and landing run. Other variables will be covered in future lessons. We will consider takeoff flaps first. The length of the takeoff run is affected by the minimum indicated airspeed at which the aircraft can safely fly. But the length of the takeoff run is also affected by the rate of acceleration. The minimum safe takeoff speed will be possible at the highest CL max, and this will be achieved at the largest flap setting. But large flap angles also generate the most drag, which will decrease aircraft acceleration and make the takeoff run longer. A smaller flap angle will give less CL max, which will result in a higher takeoff speed, but the reduction in drag will give better acceleration. Taking both CL max and drag into consideration, there will be an optimum flap angle that will give the shortest possible takeoff run. For jet transport aircraft, the optimum flap angle for takeoff is approximately 15 degrees. We can see that increasing flap angles result in a decreasing takeoff run. But beyond the optimum takeoff flap angle, the distance increases. What is the point in not using all of the runway length that is available? The operational advantage of using the optimum flap angle for takeoff is to carry more weight from a given runway length. After takeoff, a minimum climb gradient is required. The ability of an aircraft to climb is reduced by flaps because of the extra drag they generate. So, if the required minimum climb gradient will limit the maximum takeoff weight, a smaller flap angle will be used for takeoff. even though it will result in a longer takeoff run. If runway length is not limiting, you can see that the maximum takeoff climb limited weight will be achieved with no flaps. To reduce the landing distance, maximum flap angle should normally be used. This results in a lower minimum speed because of the high CL max, and a steeper approach path and increased deceleration because of the high drag. This aircraft has just taken off, and it is now time to retract the flaps. Note the indicated airspeed of 150 knots and the aircraft position on the flaps down lift curve. As the flaps retract, the lift coefficient decreases. Lift is now less than the weight, and the aircraft will sink. Increasing the angle of attack to keep lift the same is not an option, because as you can see from the lift curve, the aircraft will stall. Obviously, this is not the way to retract the flaps. We must trade indicated airspeed and angle of attack to keep lift the same as the weight. Let's reset the original conditions to consider the correct way to retract the flaps after takeoff. Before retracting the flaps, the indicated airspeed must be increased to VZF, the minimum indicated airspeed for zero flap. As the indicated airspeed increases, the angle of attack must be decreased to keep lift constant. Now when the flaps are retracted, the pilot can increase the angle of attack to keep the lift constant. When considering flap extension prior to landing, we can use the same principle of trading indicated airspeed and angle of attack to keep lift the same as the weight. As the flaps extend, the pilot must decrease the angle of attack. Just in case the examiners ask you, please note that to maintain level flight at a constant indicated airspeed as the flaps extend, the lift coefficient must remain constant. With the aircraft now on the flaps down lift curve, the pilot can decrease the indicated airspeed while increasing the angle of attack to keep lift the same as the weight.